Having considered the mechanism of amide hydrolysis under acidic conditions, we now turn our attention to the mechanism under basic conditions. So here's the reaction for you. We have an amide. It's going to be a hydrolysis reaction, so we have to have water in there. It's under basic conditions, so we have OH minus in there. And then the products are the carboxylate anion plus the neutral amine. So I'm going to say right up front, there is no good mechanism for this reaction. We just have to choose the least bad mechanism. And remember that this reaction requires harsh conditions. We're going to have to heat this for an extended period of time in concentrated base for it to go. So what that means, just like in the acidic mechanism, is there's going to be an unfavorable step in here that we are going to have to get over the activation barrier for. Okay, so if we want to get started with the mechanism, there's no problem at all with the first step. Like any mechanism under basic conditions, the anionic nucleophile that is characteristic of basic conditions is a good enough nucleophile to attack a neutral carbonyl group. So in this case, hydroxide comes in and attacks the carbonyl carbon of the neutral amide, and you break the CO pi bond and put the electrons onto the oxygen. This step is drawn as an equilibrium, which it is, but there's nothing unfavorable about it. The base strength after the step is about the same as the base strength before the step. Now, what happens next? Well, in the hydrolysis of esters under basic conditions, what we saw happen was the tetrahedral intermediate would collapse, reform the CO double bond, and then kick out OR minus as the leaving group. In this case, if we were to do what is completely analogous, we would kick out CH3NH minus as a leaving group. I'm going to say that is not a reasonable step. CH3NH minus is just too strong of a base. Okay, its conjugate acid is going to have a pKa of about 35 to 38. That is too strong of a base, and it's just not going to be kick-outable as a leaving group, even under basic conditions. Okay, so we're going to cross off that possibility. Now, another possibility is under basic conditions, another molecule of OH minus can come in and deprotonate the OH to form a dianion. Well, this is actually reasonable. You're deprotonating an OH with an OH minus. Equilibrium constant for that will probably be pretty close to 1. And in fact, I have seen this as being the next step in some textbook mechanisms for this reaction. However, as far as I'm concerned, I don't actually want to go that way because this doesn't seem particularly helpful. You're putting another minus charge in it, yeah, okay, it could happen, but how is that going to get us any closer to expelling a leaving group? What I am going to propose is what actually happens next is an intramolecular proton transfer from oxygen to nitrogen. Okay, you'll see the step on the next slide. Now, you may be cringing at that. You may be cringing at that for a number of reasons, but the initial thing that you would think is, well, we're taking a neutral amine and trying to deprotonate a neutral alcohol with it. That's not going to happen. That's unfavorable by 6 pKa units. And I cannot deny the fact that it is unfavorable by 6 pKa units. But there's a big difference between being unfavorable by 6 pKa units and being unfavorable by 11 pKa units, which are things that I'm going to say will not happen, or even being unfavorable by 20 pKa units, which would have been option 1. 1 molecule in a million will undergo this proton transfer reaction, but if you think about how many molecules you have in solution, on the order of 10 to the 20th molecules, 1 in a million is still a significant number of molecules that are going to undergo this reaction. Okay, so here's the step. Intramolecular proton transfer, so the nitrogen takes its electrons, pulls off the hydrogen, you break the OH bond, and put another minus charge onto the oxygen and plus charge onto the nitrogen. Okay, so that intermediate may look ugly because it has 3 charges on it. But the point I would like to make is it doesn't actually look that different from the intermediate after the first step of imine formation, right there, where you have a positive charge on nitrogen and a negative charge on oxygen in almost the same relationship with each other. In fact, the only difference between that intermediate and the one I'm proposing right now is this extra anionic oxygen. In the imine formation mechanism, you have a hydrogen or maybe a carbon, if you started out as a ketone, bound to that central carbon. Here you have another O- bound to the central carbon. But I'm going to make the case that that extra O- is actually okay because we are under strongly basic conditions in this reaction, and in imine formation, we were under weakly acidic conditions. So while it may look ugly, I think this is the least problematic of all of the possibilities, and it does get us towards where we need to go. I have indicated with the equilibrium arrows that it's going to favor the left, but for those molecules that can make it to the right, the last step now is going to be the expulsion of the neutral amine, as opposed to the amide anion, as a leaving group. And this last step solves virtually all of our problems. Okay, so it gets rid of 2 charges. The O- comes down and reforms the carbonyl. The nitrogen with a plus charge ends up becoming neutral. We still have 1 O-, but this is now a carboxylate anion, which is a much weaker base than an alkoxide anion is. Okay, so this last step is very favorable. It's going to drive the unfavorable prior step and, in fact, drive the entire reaction to completion. Okay, so we have examined the mechanism of amide hydrolysis under acidic conditions and under basic conditions. And hopefully you can recognize that this reaction is difficult to carry out, but it is possible to carry it out. And in the body, when it needs to be carried out, you have enzymes available to you, and the purpose of enzymes is to lower the activation energy of unfavorable steps. Okay, so that's going to end our tour of the traditional carboxylic acid derivatives, but I have a few more videos for you in this unit where we will study phosphorus esters and thioesters, which are the molecules similar to carboxylic acid derivatives that are most relevant in biochemistry.